Hello, this is Team FM Approvals, and our project is Automated Response Time Measurement for Gas Detection Equipment. Our technical director is Patrick Byrne. Here's the team. Drew Phillips, which is me, I'm an electrical engineer with my teammates Andrew Vos, electrical engineering, Andrew Ramirez, computer engineering, and James Rapala, computer engineering. For a little bit of background, FM Approvals is centered out of Norwood, Massachusetts. Their FM approved stamp is recognized and respected worldwide due to their excellent third-party testing and certification services for loss prevention equipment. The equipment that we work with is gas detectors. Here's the current setup that FM Approvals uses for testing the gas detectors. As you can see, there is a gas inlet valve here and a large valve here, which are both manual valves. The gas detector is placed here, and in the lower chamber, there is water that is connected with a tube to the upper chamber. For a little demonstration how this works, I'll show you this animation. Here's the gas inlet valve here, which is connected to a test gas tank. Once an operator opens that valve, test gas will be built up into the lower chamber, which pushes the water down and up into the upper chamber. Once the water level is reached in the upper chamber, the operator will close the test gas and be ready to record the results gained from the gas detector. The operator will then open the large valve, which allows for the test gas to escape up to the gas detector, which allows water from the upper chamber to flow down to the lower chamber, as seen here. While this is all fine and dandy, FM Approvals aims to automate this testing process. This will be done by 1. Removing manual valves and automating them. And secondly, they would like to automatically and reliably allocate the data with the computer. And, good for us, the anticipated best outcome was achieved, as you can see the difference in hardware between fall of 2019 and spring of 2020. FM Approvals expects superior testing results, which means they will gain more accurate and reliable results, which yields better proposals for their customers. Plus, they expect up to $20,000 in savings per year. And this new apparatus has the opportunity to become the standard in gas detector testing, nationally and possibly internationally. Here's a block diagram depicting the overall process for how the apparatus works between all the different systems involved. I will be talking more specifically on the valves and how we control them. Valve automation. This is done by 2 different types of valves. The first is a knife gate valve. This valve is operated with an air compressor, which allows for a very, very short actuation time. And the second type of valve is a solenoid valve. This valve also has an extremely short actuation time. And this short actuation time is critical for our project because it allows for a very consistent flow of test gas whenever any testing is going on. All the valves are controlled with an Arduino. This Arduino is coded with something similar to what you would think a finite state machine would work. This testing process would begin with pressing a start button. Then the Arduino allows for the gas inlet valve to be opened, allowing test gas to reach a certain level in the upper chamber. Once that level is reached, the flow of test gas is stopped, and the knife gate valve opens, allowing test gas to reach the gas detector for a testing time of 60 seconds. Then, after an additional 30 seconds, the lower chamber is purged of any residual test gas, which is left in the lower chamber, and then the system waits again for the start button to be pressed. For more, I'll pass it on to Andrew Vos.
Hi, my name is Andrew Vos, and I'll be talking about the PCB design for our project. In our first attempt to automate the system, we began using standalone components. An Arduino Mega, shown to the left of the screen, was used to control the system as a whole and send signals to the relay module. This relay module would then tell the solenoid valves attached through these wires when to open and close. We then connected these through a power bus to a 12-volt supply. Once we began testing in this configuration, we began designing schematics and a printed circuit board. With designing a PCB, we were able to consolidate all of the standalone components into one compact system. This is the final layout of the board design. It measures 3 inches by 4 inches and can be easily placed in an enclosure and mounted underneath the upper chamber of the apparatus. The board design features an Arduino Nano, shown here, and relays that are used together to control the opening and closing of the automated valves. A BME 280 sensor was also incorporated into the design, and it takes measurements of the ambient temperature, pressure, and humidity. Terminal blocks were placed at the lower portion of the board, which allow connections of the necessary inputs and outputs, such as the solenoid valves and gas detector. Next, Andrew Ramirez will be talking about the communication and displaying data.
To go more in depth with our GUI, we'll be discussing the communication with the Arduino and displaying the data. For our project, we have the Arduino, which will read the lower explosive limit percentages of the tested gas detector and also read the ambient temperature, humidity, and pressure from the BME 280 sensor. We'll also have our graphical user interface that was created to begin and control the test process. We'll also need to display both the lower explosive limit and ambient readings onto the GUI itself. We achieved the necessary communication between the Arduino and our GUI using serial port communication. This allowed the GUI to read any of the information that the Arduino is printing out, and not only that, but we're also able to write to the Arduino from our GUI. This means we can send a serial write that would allow the Arduino to begin the next state of the test. As you can see here, this is what our GUI looked like during the symposium. We created this GUI using C# and Visual Studio. We were able to create a serial port communication that says connect to interact with the Arduino to confirm the communication was opened. We displayed a small text box shown here, and here's the connect button as well. We also implemented a real-time graph that plotted the lower explosive limit percentages every half second and used a stopwatch that would indicate the length of the test. To further improve our GUI with the Arduino, we created a functional progress bar, as shown here, that would be run during the lower explosive reading part of the test. We also corrected the stopwatch to only begin and end during this reading as well. Once we had our BME 280 sensor, we updated our Arduino code to properly read the ambient humidity, temperature, and pressure. Once those values were read, we then displayed that data onto the GUI as shown here. Besides adding those key features, we ensured that the GUI displayed all necessary data during a test run, such as the customer name, the project ID, the gas being tested, the test location, test equipment, what you want to export, and including the test report outputted path. Once all that information is entered, you would then begin the test by pressing the start button, and the information will then be stored, which Jane will now further explain.
Hi, my name is Jane Tripala, and I will be talking about the database and the file exportation part of our GUI. So here is our spring version of the GUI again. And right where the arrow points to is showing our updated file browser. So once you hit select, you can choose the place where you are going to export test run files. This helps a lot if you're trying to export things to a USB. Next thing that is shown is in the blue rectangle is the export table. So here with the checkboxes, you can indicate whether you would like a CSV or an Excel file to be exported in the path that you had just selected. The default for this is an Excel file as requested, and this file can be used later to create graphs. The GUI also in the bigger blue rectangle also shows the database entries. And all this information is being stored to a SQLite database where its small footprint can handle multiple entries. So for the data acquisition, compared to our fall version, the log file is removed and has been replaced by the SQLite database that is displayed on our GUI. So right below, you can see the project ID, date, customer, test location, test equipment, gas type, ambient temperature, pressure, and humidity. This is recorded through the entries made in the text boxes. This is a great record to show all the runs that have gone on for more than 2 weeks. And this picture on the right is a screenshot of the CSV/Excel output. So over here we have the ID. So this helps remember how many entries were taken in from the Arduino itself, the timestamp, and the LEL percentage. All of this helps exceed our anticipated best outcome. And this was actually made possible by using a GitLab repository to store all of our work in a centrally located place. And despite coronavirus difficulties, we were able to get a large portion of this done. Yeah, we will be doing a live demo of our GUI with just highlighting all the features that it includes. So the first thing that we're going to do is just have a peek of the file browser. We're just going to leave it at the default. Then we're going to just modify the USB port on which the Arduino is going to use to connect to. We're going to make sure that connects a little bit later on. But the next thing that we're going to do is just fill out the text boxes. So we're going to fill out the customer name, the project ID, the test location, and the test equipment number. Then we're just going to use the dropdown to change the gas. Next thing that we're going to do is just choose which file we're going to use for our table. And we're just going to click connect. We'll wait a couple of seconds so that we can get the readings for the ambient temperature, humidity, and pressure. As you can see, they've already popped up. Then we'll press start. Arduino will go through the states and then just start collecting values for the LEL percentage. As you can see, the stopwatch has already started and it will stop at 60 seconds and the progress bar will continue until the process is done for collecting the values. The next thing that we can do is we can actually view the database table. So once we click on it, we can scroll through all the entries and you will see the project ID, date, customer, test location, test equipment number, gas type, and all the ambient measurements. So this is a good way of recording our data instead of the log file that we used in the fall. So now that our stopwatch is done, this GUI actually has already generated our Excel file, and we will be able to find it right where we had selected. So open it up, and you can see that it has the appropriate headings for ID. This kind of just keeps track of how many entries we've collected, the time of which they were collected, and the LEL value. So these values can later be processed in Excel, and they could give a graph that is more detailed than the one that was displayed on the GUI. We would like to give a big thank you to Patrick our technical director, Dr. Sunak, and Alex C. Petrillo, our consultant technical director. Without their help, we wouldn't have been able to achieve our anticipated best outcome.